Hello everyone, this is a short presentation by Lyutikov, and this is the work I am doing with Sergei Cherkis from Institute of Advanced Studies and University of Arizona. Magnetic topology in coupled binaries, spin orbital resonances and flares. And what we have in mind is that magnetically coupled binaries, for example merging neutron stars, can produce precursors due to the mergers. But if they produce persistent luminosity, the expected power is not very large. For example, if one star is only magnetized, then it's L1m, and if both, it's L2m, and they're pretty small. So not much, only if beamed or in radio. What about flares? The question we are asking, are there quasi-static spin orbital configurations that would be slowly twisted and then can release this twisted energy in a flare? So, and there is a known basic, let's call it basic Z resonance, omega 1 plus omega 2 equals 2 omega. So for future reference, the plane of the orbit is xy, and pulsar 1 is on the left, pulsar 2 is on the right. Their magnetic moments are counter-aligned, so they are coupled. And let's first do the basic rotation around Z. And here is our untwisting configuration. And if you can see that both stars are twisting and both stars are spinning, and the spin is undone by the orbital motion. Okay, so other interesting configurations. For example, Y spin. Now the star number 2 will be spinning along y-axis. So we do one spin along y-axis, then half an orbit, another spin along y-axis, another half an orbit, and we are untwisting. Very good. So let's look at this again. So we do one twist, one spin around y-axis, another half an orbit, around another spin around one axis, and we are supposed to untwist. Oh, never mind. Did you get the trick? Another interesting case. Now we are spinning along x-axis, and we already know that we need two spins. So let's do two spins. 1, 2. And orbit and a full orbit, and voila, we are untwisted. Yeah. So let's look at it again. So we need two spins and one orbit. So here is one spin, here is half an orbit, here is another spin, here is another half an orbit. Trouble. So, if you look at it from the topological point of view, so the direction of magnetic field from point 1 to point 2 is a path on a two-sphere. We're not interested in the twist of each field line, which is curl B. For example, you can think that each hair in a braid can be twisted, but we're interested in braiding, not twisting. How many bundles does it take to make a braid? 3, right? So we need to track 3 points on a two-sphere of magnetic field direction. And we'll do the following. So we have point O, which is the direction of the spin of 1. Point A, which is the direction of the magnetic moment of 1. And point B, that's the radius from 1 to 2. Okay, and we're gonna track this angle from O to A to B. And we're kind of cut it in the middle, so we're not thinking about the same thing will be happening around second finishing point. So, and here is how it works. We have the same spins, and you see that that angle remained constant, but in a little bit different configurations. Look up, it flipped. So again, we are tracking this angle, and right here it flipped. That's the twisting. So this illustrates 2 points. Recall the problem we had with the Y spin, and that's the topological, we call it topological bifurcation when points A and B overlap. And also recall the example with the X spin. Depending on the phase of how we start, the angle may or may not flip. Okay, so, and we are all thinking about precursors to LIGO. So there is a global untwisting resonance, and there are numerous locally untwisting braids. And those locally untwisting braids can produce differently modulated signal because of the phase. Sometimes it flips, sometimes it doesn't. And generally it may release a fraction of the total magnetic energy when they are twisted by the order of unity. So for example, for 10 millisecond pulsar, this resonance occurs at -2 seconds. Thank you.